And good afternoon. I warmly welcome you to what we call the European edition of the One World Signal Processing Seminar Series taking place this fall. And today I'm very happy that we have the kickoff talk by Fernando Gama. Welcome, Fernando. My name is Marius Pesavento. I'm professor at TU Darmstadt in Germany. And together with my colleagues, Erik Larsson, Christoph Mecklenbreuker, and Christos Masouros, and with the great support of our colleagues from the Chinese University of Hong Kong, Hoito Wai, Chunghui Chang, and Winking Ma, we have set up an exciting program that you find on the One World Signal Processing Seminar website. I hope you like it. And this edition will feature mainly 14 webinars by distinguished speakers in the area of signal processing, with the main focus on signal processing and learning methods for wireless communications, but also for other applications. So we practically have one seminar per week in the following weeks, mainly on Wednesdays, except next week. So take note of this. Next week, Mewan Deba will have its seminar on a Thursday, and also later in November, Christoph Studer will have his talk on a Tuesday. So I invite you to check regularly the website regarding the schedule. So before we start, let me leave a few words about the organization of these seminars via Zoom. I ask you to mute your microphones if you have not done so already. If you have questions during the talk, then feel free to type them in the chat. We will collect all the questions in the chat and then address them at the end of the talk. Then you will also have the chance to ask further questions. So after the talk, in the Q&A sessions, you will have the chance to digitally raise your hand with a button. And when we call you, you unmute your mic and ask a question. Alternatively, of course, you can simply type your questions and we will read it out loud for you. So let us start. So let me briefly introduce our speaker of today, Fernando Gama. And Fernando Gama received the electronic engineering degree from the University of Buenos Aires in 2013, the master degree in statistics from the University of Pennsylvania in 2017, and the PhD degree in electrical and system engineering from the same university in 2020. He was a visiting researcher at TU Delft, the Netherlands, in 2017. And since the Netherlands lie in Europe, practically this qualifies him to appear in the European edition of these seminars. After this PhD, he became a postdoctoral scholar at the University of California at Berkeley, and he's now a postdoctoral research associate at Rice University. His research interests are in the field of information processing and machine learning over network data. And certainly, I consider Fernando as a rising star in our signal processing community. He received a number of awards and recognitions. His papers are highly downloaded and cited, and he has been awarded a Fulbright scholarship for international students in the period 2014 to 2016. So I hope you all enjoy this seminar, and without you, I would like to hand over to you, Fernando.
Thanks a lot, Marius, for the introduction. So yeah, hello, everyone. I, of course, would like to thank for the invitation, for the introduction, both Marius and all the organizers for putting this seminar together. Before I begin, I would also like to thank my collaborators that are listed here, of course, without whom this work wouldn't have been possible. So basically, the idea is that today I'm going to talk about graph neural networks, mostly from a signal processing perspective and understanding. This talk is more or less like a short tutorial on GNNs for those of you that are not entirely familiar with the topic. The idea is that I will set like a common framework of reference for GNNs and cover the basics of them. And I hope that this will help us have like insightful discussions in the Q&A part of the seminar. So the reason why I've been working on graph neural networks is because we want to do machine learning on graphs. And the reason we want to do machine learning on graphs is because graphs are genetic models of signal structure that can help to learn in several practical problems. to illustrate the practical relevance, let me show you some examples we have worked. In authorship attribution, for example, we have networks with nodes representing words and edges whose strength represents how often a certain author uses those pairs of words. As it happens, different authors use pairs of words with different frequencies. So it follows that these graphs are different for different authors and can thus be used to learn the authorship of unattributed texts. In recommendation systems, we have these graphs where nodes are movie ratings and edges represents rating similarity. So for example, on the left, we have a user whose ratings vary substantially, and on the right, one whose ratings are more uniform. And these graphs can be used to learn a prediction of the rating of unseen movies. Now, these are certainly interesting problems, but the kind of problems we are more interested in are those involving physical graphs. One such example are wireless networks, where the nodes are transceiver and the edges represent the communication channels, and we can leverage the resulting graph to learn optimal resource allocation. In this video, we see another example where we have these robots that need to coordinate their velocities to fly together while avoiding collisions. In such a scenario, there are two graphs, one describing physical proximities and one describing the communication network. And both of these graphs are useful for learning suitable controllers. As a final example, we have smart grids where each node is either a consumer or a generator, and the grid has to keep the balance between the power generated and the power consumed. This balance is determined by a highly nonlinear system that depends on the actual topology of the grid. Therefore, the graph representing this grid topology has to be useful for learning power generation. So these are 5 quite dissimilar problems, but that they all require information from the graph structure in order to be successfully solved. Therefore, I postulate that the core of machine learning on graphs is about exploiting this graph structure. Now, there is a very well-known example of successful machine learning that leverages the structure, and those are convolutional neural networks. GNNs are very good at learning over regular data, and they are good because they scale, they exploit the data structure, and they have an efficient implementation. And all of this is granted by the use of the convolution operation, which is central to the field of signal processing. However, we want to do is learn on graph data, which is not the one GNNs are suited for, precisely because regular convolutions don't work on this type of data. So what we need to do is to use graph convolutions, which are central to graph signal processing. So in essence, if we want to succeed at machine learning on graphs, we must find architectures that scale, exploit the data structure, and have an efficient implementation. This architecture is precisely that of graph neural networks. As is the case with GNNs, GNNs are built from graph convolutions that are local and distributed linear operations that generalize time convolutions. So this in turn makes GNNs the appropriate generalizations of CNNs. Now, GNNs defined this way are local and distributed, which is great, but this is certainly not enough to justify that they are a good choice. We also need them to scale. And to get to scalability, we will prove the properties of permutation, equivariance, and stability. Permutation equivariance means that GNNs effectively exploit the data structure, while stability guarantees similar results on similar graphs. Together, they will give us transferability and scalability. And finally, as a brief illustration on what GNNs can do, we will show you one application to collaborative intelligence, which is the problem of flocking. That is, in this problem, we have a team of agents that need to collaborate to accomplish a global task. That is, they need to fly together at the same velocity while avoiding collision. The issue is that the agents are autonomous, which implies that they take decentralized actions based on partial information, and yet they need to accomplish a global task. What I will show you is that GNNs are the key enablers for solving this tension between a global objective and local action. Good. So to introduce and formally define graph neural networks, we first need to set the mathematical framework that we are going to use for describing graph structure data. So to better understand the definitions, let's start by drawing parallelisms with discrete signal processing. So basically, data in signal processing can be described in terms of a discrete time signal, which I have pictured here on the left. Now, choosing to model data this way imposes a strong, yet implicit assumption that the relation of nearby values carries information. So for example, if 2 consecutive values change much, we know that we have high frequency content. But if two values that are far apart change much, we really don't have much to say. So as we can see, the structure is implicit, but we use it all the time. Now, when we consider graph structure data, we need to make this relationship between the values explicit. And in the case of discrete time signal, for instance, we can do this by considering this structure, where we're explicitly saying that one value is related to the next one by a shift in time. This support is a graph that is known as a directed path. So now that we have defined the two constitutive elements of signal processing, that is the data structure and the signal value. Know that in traditional signal processing, we assume the data structure is that of time, and we care about processing the corresponding signal values, but we're always implicitly exploiting this data structure. Now, we want to generalize these two graphs as a means of describing more complex data structure. So to do this, consider a graph G, which is comprised of a set of nodes or vertices B and a set of edges E that capture the pairwise relationship between the nodes. Then we define the graph signals by associating a value to each node. So now the relationship between signal values is given explicitly by the graph G. Now, to be able to mathematically operate with signals defined on top of graphs, we need a matrix representation of the graph. For example, the adjacency matrix that sets a 1 on the element ij if and only if node I is connected to node j. So here we see the adjacency matrix of the directed path, where basically only non-zero elements are below the main diagonal, and this reflects how each signal value is related to their immediate nearby signal value, which describes the passing of time. Now, for this arbitrary graph below, we have quite a different adjacency matrix that we can see symmetric because the graph is undirected. Another example of widespread use in the literature is the Laplacian matrix. But in any case, note that when we choose to describe the graph by a matrix, we are fixing the ordering of the nodes, and the mapping between all possible orderings is obtained by using permutation. In what follows, we consider the matrix representation of the graph to be a generic matrix S that has a sparsity pattern that respects the sparsity of the graph. We can think of this as the adjacency, as the Laplacian, or as any other matrix that respects the sparsity pattern of the graph. So we said that graph neural networks are built upon graph convolutions, and that graph convolutions are generalizations of time convolutions. So I will take the license to remind you all what a convolution is, right? So a convolution is a linear combination of shifted versions of the signal X. We shift the signal through time, and for each shift, we weigh by a different coefficient X. And if we want to extend this concept to graphs, we need to have a notion of shift. This notion of shift is defined in graph signal processing to be precisely the matrix description S of the graph that I just mentioned in the slide before. Note that if we apply the adjacency matrix S to the directed path signal X, we are indeed shifting the signal in time, or in the context of graph signal processing, we're shifting it around the graph. So basically, the traditional notion of shift in time is equivalent to applying the shift S of a graph. Now, let's consider an arbitrary graph now. Here we have this graph with 11 nodes and the different signal values on top of the nodes of the graph. Each time we apply the shift, we are guiding information from nodes that are farther away. The first image here is X, and the second image here is SX. And in red, we're showing nodes that node 1 can reach by successive application of the matrix S. Here is the second application of the shift and the third application of the shift. So basically, for each different shift application, we weigh the resulting signal by a different coefficient or filter. So a graph convolution is a linear combination of shifted versions of the signal, the same as in time. It's just the notion of shift that has changed. The result is that the graph convolution is assigning different weights to information located in different neighborhoods. Very important is to note that the effect of the shift operator is to update the signal with a linear combination of neighboring values, which means that this operation is entirely local. That is, that there is not need for a centralized unit to compute the graph convolution operation. Now that we have defined the notion of graph convolution, or equivalently this graph filtering operation, we can proceed as in traditional signal processing and find the best linear filter that exploits this structure. So we're given a graph matrix S that describes this structure, and we proceed to find the filter types HK that minimize some loss function J. However, linear models have limited representation power. So what we would like to do is to move to nonlinear graph signal processing. And the most straightforward way to do this would be to include a pointwise nonlinearity at the output of the graph convolution. And as a matter of fact, this defines a graph perceptron, which is a basic nonlinear processing unit that consists of a graph filter followed by a pointwise nonlinearity. Then we can proceed to learn these graph filters by finding the tops that minimize the loss function J. Same thing. Now, this is still quite a basic nonlinear description of models, so we can increase the representation power by repeating this structure in cascade. And this is exactly what defines a graph convolutional neural networks, or GNNs, which are a cascade of layers, each of which is a graph perceptron. That is, it applies a graph convolution followed by a pointwise nonlinearity. So here in the diagram, we have a single graph perceptron where we take the input, apply the filter characterized by these tabs H1, and then apply a nonlinearity to obtain an output X1. This output is then fed into another graph perceptron, which is layer 2. This new graph perceptron is characterized by different filter tabs H2, which filter the output of the previous layer, and once filtered, a new nonlinearity is applied to obtain the output X2 of the second layer, and we keep repeating this for as many layers as we want. The GCNN depends therefore on the filters H, which we learn from training data, but also depends on the graph structure S that is typically given by the product. So in short, a GCNN is a nonlinear mapping that exploits the underlying graph structure S. It relies on local information only and has a distributed implementation. Now, so far, graph signal assigns a single scalar to each node. Like we see in the example here that each node supports a different signal value. And we can conveniently describe this signal value as a scalar and concatenate all these scalars, one for each node, on a vector X. Now, we can extend the descriptive power of graph signals by assigning a vector to each node instead of just a scalar. For instance, when we associate a vector of dimension 2, now the graph signal becomes a matrix X, where each column represents a scalar graph signal. And we can keep adding entries to the vector associated to each node, which amounts to adding columns to the matrix X. Each entry of the vector is associated to a node, and we call that a feature, right? So basically, this is how we define multiple feature graph signals as a matrix X of size n, the number of nodes, times f, which is the number of features, right? The dimensionality of our data. Now, it is important to know that the row I of this matrix collects all the big F features at node I, and that this represents the information available at node I, and this information can be accessed with no need of neighborhood exchange. Column F, on the other hand, represents the feature little f collected across all nodes. This implies that each column X superscript F is a scalar graph signal, which are the same ones that I have been manipulating up to this slide, right? So the key operation of GCNNs is that of graph convolution, so we need to extend this operation to handle multi-feature signals. We know that the convolution has to be a linear operation and that it needs to depend on local information that is accessible only by means of neighboring exchanges, and that it can be implemented in a distributed manner. So the convolution operation acting on multi-feature graph signal is the one that I have written here in this equation. And to see why this is the case, let's analyze what's going on in these equations step by step. So let's start with S times X. Basically, we have X, which is our multi-feature graph signal, where each column is a scalar graph signal representing each feature. And we have S, which is the matrix representing the sparsity pattern of the graph. So for instance, it could be the adjacency matrix or the Laplacian matrix. Now, we see that the multiplication of X by S on the left is actually shifting each graph signal feature. So we're taking each row of S and using its entries to compute a linear combination with the entries in each column of X. Now, since each column of X is the scalar graph signal representing each feature, and since each row of S represents the sparsity of the graph, what we're actually doing is a linear combination of the values of each feature that are located in neighboring nodes only, and that is due to the sparsity pattern that S has. Now, let's include the matrix H. This matrix replaces the scalar filter tab that we used in graph convolutions, right? So before we had a scalar filter tab, and now we have a matrix. When we multiply X by H on the right, we see that we're doing a linear combination of features at each node. That is, we take each row of matrix X, which corresponds to all F features at each of the nodes, and do a linear combination of them with the entries of the filter tab in each of the columns. Now, when we multiply X by a matrix on the right, we are doing linear operations that do not involve any neighbor exchanges. So these linear operations can be computed internally by each node. Good. So now we see that this operation is, in fact, the appropriate convolution operation for dealing with multi-feature graph signals. But how does it relate to the typical graph filtering convolution that we use for scalar graph signal? Well, without going into much detail, just think of this convolution operation as basically being equivalent to the application of a bank of graph filters. So we have an array of graph filters, and we apply them to all different features and combine them accordingly. So basically, the convolution operation on multi-feature graph signals is nothing more than the application of a bank of graph filters on the single feature signals. What's most interesting here is that this operation allows to map graph signals with features of different sizes, and this is given by the shape of the matrix HK. But basically, the main idea here is that the graph convolution in a multi-feature case is a bank of graph filters, right? And bank of filters is something that we're familiar with. So now we can use this extension of graph convolutions to define the general GCNN that we will be using from now on. So we know that a single feature GCNN is defined as a concatenation of layers, each of which applies a graph convolution followed by a pointwise nonlinearity, as we have in this equation. In this case, the XL is a vector of size n, HLK is a scalar representing the k learnable filter tab at layer L, and S is the given data structure. One brief comment is that in machine learning, hyperparameters refer to values that are design choices, as opposed to parameters, which are the ones that we learn from data. So in this case, hyperparameters are the number of layers that we want and how big our filters are going to be, and the parameters are the filter tabs themselves. Now, when we move to multi-feature signals, all that we need to do is to replace the convolution by the operation that I presented in the previous slide. And here we see that the multi-feature GCNN is basically the same, except that now XL is a matrix, and so is HLK. And the size of H determines the number of features that we will have on each of the layers. Here, there is a summary of the most popular architectures that are out there in the literature. The only point that I have here is to just show that all these architectures are just particular cases of this GCNN equation that we have on the top of the slide. I won't go into detail on all the equivalences, unless, of course, you want me to, but I would like to mention that, there is this famous oversmoothing problem going on in the literature, but this is not actually a problem. I mean, this notion of oversmoothing that everyone talks about, it just arises from the fact that GCNs, right, which are here on the fourth line, they are forcing all the filters involved to be low pass. And they do that because they are forcing them to learn a single coefficient. If instead we free the GCNN to learn all the filter tabs, even if it's of order 1, we don't have oversmoothing anymore. So this notion of oversmoothing is just like a self-fabricated problem by forcing the learned filters to be low pass. So basically, in general, this is the general equation of GCNN, and that won't restrict your representation space in any possible way. Now, more generally, we can describe graph neural networks as nonlinear signal processing tools that consist of a cascade of blocks, each of which applies a graph filter followed by a nonlinear activation function, right? And we know that graph filters may or may not be convolution. So basically, if this filter is either an FIR, an IIR, or an ARMA filter, we will have a graph convolutional neural network. But if this filter is a node variant graph filter, for example, we have a node variant GNN, which is non-convolution. And another example of a non-convolutional GNN is if we adopt an edge variant graph filter, in which case we end up having what we call edge nets. Edge nets are basically the most general neural networks that still preserve the local and distributed nature of the architecture. We can even relax the constraint that the activation functions be pointwise, and we can start using nonlinear graph filters as activation functions. So the whole point of this slide is that when we think of GNNs as extensions of filters, we have decades of research in signal processing that we can leverage to our own advantage. In any case, from now on, I will focus on graph convolutional neural networks, and I will just refer to them to GNNs to make it short, right? But remember that basically GNNs are filters followed by nonlinearities, right? And everything that we know about filters still helps, still works. So to get back, graph neural networks are signal processing architectures that exploit the graph structure, rely on local information, and have a distributed implementation. But is this enough to have a good signal processing tool? Well, it is not. And as a matter of fact, there has been a lot of discussion on what is the appropriate graph operation to use, right? As evidenced by all the architectures that have been popping up. And the problem is that beyond Euclidean domains, we can rarely proceed out of intuition. So we generally need to operate from first principles. What we do know is that the regular convolutional neural networks are good at machine learning because they are translation equivariant and stable to small deformations of the domain. In graphs, translation equivariance is analogous to permutation equivariance, which allows GNNs to exploit internal symmetries of the graph. Stability to graph perturbations, on the other hand, implies that similar graphs will yield similar outputs. And these are two fundamental properties that characterize the representation space of GNNs and together lead to scalability and transferability. So recall that the graph convolution operator is a polynomial on the shift S, which depends on the filter parameters H, on the shift operator S, and is applied to the input signal X. Then we can state that graph convolutions are equivariant to permutation. What this means is that for graphs with permuted shift operators and permuted graph signals, it holds that the outputs are permuted versions of each other. The proof follows from basic algebra and the properties of permutation matrix, so nothing very complicated here. Now, since GNNs are a cascade of graph filters with pointwise nonlinearities, and since pointwise operation does not mix node values, then the GNNs must retain the permutation equivariance property. And this is exactly what we're stating formally in the following theorem. So basically, for graphs with permuted shift operators and permuted graph signals, it holds that the output of one GNN is a permutation of the output of the other GNN, of course, as long as they are using the same filters H. But essentially, what this means is that signal processing with graph neural networks, with graph convolutional neural networks, is independent of labeling. So the point here is that this invariance to node relabelings is what allows GNNs to exploit internal symmetries of graph signals. So consider the two pictures shown here. As we can see, based on the labeling of the nodes, which is given by the numbers, these two graph supports are exactly the same. And what this means is that the matrix S that describes both graphs is the same. What is different is the graph signal defined on top of them, which is shown here in different colors. So the graph signal in A is different from the graph signal in B, which means that vectors X in each case are different. However, we can take this signal in B, rotate it 180 degrees and turn it inside out, and we end up with a signal, with an image that looks exactly like the signal in A. It's just that the labeling that is different. So what this means is that although different, the signals on A and B are actually permutations of one another. So if we have an architecture that is permutation equivariant, what this means is that this architecture, the GNN, can learn to process B just from seeing A in the training set, which of course leads to faster training by leveraging the structure to learn multiple scenarios from a single sample. Now, permutation equivariance, of course, is an important property because it what allows GNNs to exploit the graph structure to generalize better. And while real graphs don't usually exhibit perfect symmetries, they might still have substructures that are close to permutations, right? As we will discuss shortly in some of the applications. Now, the thing is that permutation equivariance is a property of graph convolutions that is inherited to GNNs. So why bother in adding pointwise nonlinearities to create a GNN? Or more specifically, what is good about the pointwise nonlinearities? Or similarly, what is wrong with linear graph convolution? So briefly, the problem is that linear graph convolutions can become unstable to perturbations of the graph if we push their discriminative power. And that the advantage of adding the pointwise nonlinearities is that they will make the GNNs stable to perturbations while retaining this discriminability. And what's very interesting is that these questions can actually be answered with an analysis in the spectral domain, which is a trademark approach of signal processing. So a graph convolution is a polynomial on the shift operator. We can decompose the operator S as V lambda V Hermitian to write the spectral representation of the graph convolution as a projection of the output on the eigenbasis of S. We see then that the graph convolution is a pointwise operation in the spectral domain because of the diagonal nature of this matrix lambda that we have here. And this notion that the graph convolution is a pointwise operation in the spectral domain, of course, is the same notion that we have from time convolutions and their Fourier representation. Now, what is interesting here is that this operation is determined by the graph frequency response, which is a polynomial that is acting on each eigenvalue lambda I of the matrix S. But this polynomial for every lambda I has always the same filter taps hk. So we can reinterpret the frequency response as a polynomial on continuous lambda. So here we have in this black solid line the value of the polynomial throughout the spectrum. And in blue dots, what's the value that the frequency response takes when instantiated on a specific graph where the eigenvalues are given by the ones that are drawn in blue here. Now, if the graph changes, the eigenvalues change. And therefore, the places where the frequency response gets instantiated will change, as we can see here in red. However, the frequency response as a function of continuous lambda, this black solid line, is the same and hasn't changed. So the key insight here is that the frequency response is the same no matter the graph. And the actual effect of the graph on the output is observed when instantiating the frequency response in the particular spectrum. Now, of particular interest for this part of the talk are these graphs that we call integral Lipschitz. So basically, these are graphs whose frequency response satisfies that lambda times its derivative is bounded by some constant c. This is reminiscent of wavelets, right? So basically, what we are saying here is that integral Lipschitz filters have to be wide for large lambda, because if lambda is big, then the derivative has to be small, so the filters cannot change fast. But they can be thin for low lambda, so that the derivative can be very big and still satisfy this integral Lipschitz condition. So what this means is that the filters can change very fast for low values of lambda. And these filters are of interest because they are the ones that are stable to perturbation. What do I mean by perturbations? Well, we will measure perturbations as the relative distance between the original graph S and the perturbed graph S hat. And we define this relative distance as the norm of the smallest matrix E that maps S into a permutation of S hat. So basically, this distance measures the relative differences between graphs modulo permutation. In particular, it will be small if the graphs are close to being permutations of each other. And the reason for this is that we know that if the graphs are actually exact permutations of each other, we're expecting to have the exact same response. So now we are in position to get a stability result when these GNNs are used with filters that satisfy the integral Lipschitz condition. So consider GNN with L layers having integral Lipschitz filters HL with constant C. Graphs S and S hat are such that their relative distance is less or equal than epsilon over 2. And then it holds that for all signal X, the difference in the output between a GNN that runs on S and one that runs on S hat, both GNNs with the same set of filters H, this difference is bounded by epsilon, which is the distance between S and S hat. So in essence, GNNs can be made stable to graph perturbations if filters are interrelated. So what do we mean here? This GNN stability theorem holds for any relative error matrix E. But the particular case of edge dilations will give us very valuable insights on what's actually going on. So in edge dilations, we multiply edges by a 1 plus epsilon for a small value of epsilon close to 0. So basically, an edge dilation just produces a spectrum dilation, that is an increase of epsilon in the eigenvalue. As we see in this image, small deformations may actually result in large filter variations for large lambda if the filter is not integral Lipschitz, right? So the filter that we have here is not an integral Lipschitz filter, and we can see that the output of the filter changes a lot for large eigenvalues when moving from the blue eigenvalues to the red eigenvalues. And if the output changes a lot due to a change in the graph, right, and remember that epsilon was small, then this doesn't qualify as a stable filter. Now, integral Lipschitz filters, on the other hand, are always stable. And this is because either the eigenvalue doesn't move, which happens for low eigenvalues, or the filter doesn't move, which happens for large eigenvalues. Now, the problem with linear graph convolutions is that they cannot be simultaneously stable to deformations and discriminate features at large eigenvalues. So basically, integral Lipschitz filters are stable because they are wide for large eigenvalues, which are the ones that typically move a lot when we have a changing graph. But what this means is that if we want to separate between frequency content located at eigenvalues that have a large value, then we do not need a filter that is flat for this part of the spectrum. Actually, we need filters that can be narrow enough to separate the information on one eigenvalue from the information to the other eigenvalue. But if the graph changes, even if it changes slightly, then the eigenvalues fall outside of the filter's passband, and therefore the output will become 0. So in summary, linear graph filters cannot be simultaneously stable to deformations and discriminate features at large eigenvalues. And this limits their value in signal processing problems where features at large eigenvalues are important. Now, the good thing about pointwise nonlinearities is that they preserve the permutation equivariance while generating low graph frequency components, which we can discriminate with stable filters. So for instance, here we see that when we apply a ReLU nonlinearity to the sole eigenvalue that we had before, now we have low eigenvalue frequency content. And that this low eigenvalue frequency content is different from the one generated by the signal on the other eigenvalue. So now that we have low eigenvalue content, we can design stable filters that will be able to separate them because the low eigenvalues do not change much when the graph changes. So in summary, the nonlinearity demodulates, right? It creates this low frequency content that once we have information on the low frequencies, we can proceed to process it in a stable fashion. Therefore, GNNs are stable and selective information processing architectures, whereas linear graph filters are not. Now, to wrap up the last part of the talk is I will illustrate the use of GNNs in the problem of flocking, which is a problem involving a physical network of robots. So basically, we want the team to coordinate on their individual velocities without colliding with each other. This is a very easy problem to solve if we allow for a centralized coordination, right? We just set each individual robot to play with the average velocity of the team, and we're done. But it is very difficult if we do not allow for centralized coordination. And it is very difficult to solve precisely because of the information structure on this distributed system. So this partial information structure is what makes designing behaviors quite challenging. What I mean is that the partial information structure implies that node I has access to its own local information at time t, and the information of its one-hop neighbors at time t minus 1, and the information of its two-hop neighbors at time t minus 2, and so on. So in the problem of flocking, we have a team of n agents with positions ri at time t, velocities bi of t, and accelerations ui of t, where I is the index of each agent. The system dynamics is described by a zeroth order model. That is, we assume a constant acceleration held during each sampling time ts. So basically, TS is the clock of the system, and we define it as the time it takes to move from one acceleration value to the next. We have the power to control the acceleration UIT of each agent, and we are able to design a sequence of accelerations values UI of t for each agent I and for the duration of the trajectory. I agree that these are like quite simplified in dynamics, but my point here is just to be a proof of concept example on learning decentralized controllers, but more realistic scenarios can be found like in the papers that I mentioned below here. So the objective is to coordinate the velocities VI of t of all agents to be the same while avoiding collision. We measure the cost by computing the velocity variation across the team. This cost consists of first computing the mean velocity of the team, then computing the difference of velocity between each individual agent and the average velocity of the team, and then adding up over all the agents to compute the variation of the team. What we can do to coordinate the velocities is to control the accelerations UIT of each agent, and we want to do that such that the cost, like this velocity variation I just mentioned, is minimal. So recall that controlling the acceleration affects the value of the velocity by means of the team dynamics from the previous. So here we see agents illustrated by a blue dot that start flying at time t equals 0 with arbitrary velocities in both direction and magnitude, as we can see by the black arrow. We see the next snapshot at time t equals 1 second, where the agents have managed to agree on a direction, and then for t equals 2 seconds, where they have effectively managed to fly to. Now, the problem setting that we actually want to consider is a decentralized setting. So the agents can only communicate with each other if they are located within a communication radius R. This imposes a communication graph that we describe with a matrix S. Now, because the agents are moving, the communication graph changes with time, because at different times, each agent might be communicating with different. So we will denote this shift operator as S of t. The graph connections are now illustrated in the pictures below, where the gray edges connecting the agents represent, of course, the communication links. As we have discussing, we want to learn decentralized controllers, so we will use graph neural networks that respect this communication graph as a means of parameterizing the control action U. Certainly, as we know very well by now, GNNs are naturally local and distributed operations. So this will automatically mean that the learned controller U that we're parameterizing by a GNN is actually a local and distributed controller. Briefly, to respect this partial information structure of distributed systems, we have to adapt the graph filters involved in the GNN to be as shown in the last equation. This takes into account the fact that the graph may change with time and that the information that we receive might be delayed. So to train this GNN-based controller, we borrow from robotics the notion of using imitation learning. The idea here is that we have two phases, an offline training stage and an online execution stage. During the offline stage, we assume that centralized computation power is available. Furthermore, imitation learning, what it does, it proposes the existence of some expert controller that we will denote U star, that in our case is a centralized controller that is available during the offline training phase. So imitation learning, that entails finding the best parameters H such that the decentralized GNN-based controller phi is as close as possible to the expert, decentralized controller U star. In this flocking setting, we consider the expert centralized solution U star to be the one that avoids collision, and it's given by this equation. And for the sake of completeness, I clarify that the state xit of each agent is said to be the value of the gradient of potential agent. The point here is that this gradient can be computed locally, so the graph signal that we are communicating doesn't alter the decentralized nature of using a GNN, right? So, and to wrap up, I want to emphasize that the centralized controller, this expert controller U star, is required at training time, but not at testing. So the framework of imitation learning poses the availability of an expert controller. This expert controller is typically either intractable, like is our case, because we assume centralized controllers are impossible, or very hard to compute. What we do then is to pick another controller that has all the characteristics that we want, in our case that it is decentralized, and we train. during an offline stage, the controller that we want to look like the controller that we cannot have. Then once the controller we want has been trained, we can go to the online phase and deploy it without the need for the expert controller. What this means is that oftentimes we want controllers to transfer to unknown settings. So for example, if the expert controller is very hard to compute and we can only do it for a small team of agents, we want that the controller that we are learning can scale to larger teams. So we will train in a small team, but test in a much larger. So in this sense is that the properties of the parameterization that we choose for our decider controller are very important. And in this particular case, the permutation equivariance and stability properties that the GNN-based controller will have will be fundamental for the observed success of this imitation learning framework in the problem of flow. So first, I will check this idea of transferability that I was mentioning before. So basically, each sample in my training set has a different initialization, right? So here we see on the right one of the optimal trajectories. The agents start flying, and they learn to flock together at the same velocity. On the right, on the other hand, right, we have a different initialization, which means that we have a different graph. And these are the kind of things that we will see online, which we haven't seen offline. So we will need to see if our trained controller transfers, right? So as we can see here, this is the effect that the trained controller has on a setting that we haven't seen before. And we can see that indeed, the decentralized controller is able to flock this team of agents. Next, we test scalability. Basically, we want to know if we can scale up, right? So we start testing and training on 50 agents. Again, we see that this works. This is an example at the online phase of execution. So this is the learned controller that you're seeing. Here you see it for 75 agents. And here you see it for 100 agents. But more interestingly is this notion of transferring at scale, right? So we start with a training set that consists only of 50 agents. We go ahead and we test on 50 agents, and this is what we observe, as we have been discussing just now. We know this works. Now we take that exact same controller that we trained for 50 agents, and without doing anything else to that controller, we just test it on 75 agents. And we see that this is indeed working, right? We see that a controller that was trained on just 50 agents can actually be tested on 75 agents, and it works. And we can even scale up to 100 agents, right? And this still works. So this shows that we're perfectly able to train on a small team and test successfully on a much larger team. And we have scaled all this way up to 350, and it still works just perfectly fine. Good. So basically just on time, we have argued that successful machine learning on graphs requires architectures that scale, exploit the structure, and have a distributed implementation. Graph neural networks achieve this by using graph filters followed by pointwise nonlinearities. In a sense, graph neural networks are nothing more than an extension of graph filters obtained by including a pointwise nonlinearity. So it's a very straightforward way of doing nonlinear signal processing. To characterize GNNs, we have shown that they are permutation equivariant and stable to changes in the graph, which leads to scalability and transferability. And we also show that linear graph convolutional filters are either stable or selective, but cannot be both. And that the inclusion of pointwise nonlinearities is what makes GNNs both stable and selective information processing architecture. We illustrated the use of GNNs in the problem of blocking a multi-agent robot team, where we have an application to a physical network. And we observe that parameterizing the distributed controllers by means of GNNs allows the controllers to scale up and transfer. So there we are. Thank you very much for your attention, and I will be more than happy to take questions and hopefully kickstart discussions on GNNs.
Thank you very much, Fernando, for this very nice talk. Very interesting. So we have time. We have time for questions. You can raise your hand, or you can write in the chat. So
I think there are actually two questions in the chat.
In the chat, I think we see P. Shat is asking, in the definition of GNNs as a cascade of filters and nonlinearities, do all the graph convolutions rely on the same underlying graph? Nodes.
That's a wonderful question. That's a wonderful question. So basically, the question is the matrix S the same at every layer? Mathematically, no, it doesn't have to be. And in fact, we show that filters, are, like you can change the graph. That's basically what we've been showing. Now, in the framework that we're trying to understand here is this idea that we have physical networks, right? So on every layer, like you're assuming that the graph is given by the physical characteristics of your network. So typically, we will assume that the graph S is the same, or in the flocking problem, that it will change with time. But mathematically speaking, if you have like problems without or not in the realm of physical networks, or if you could model the changes in your physical network, yes, you can choose a different matrix S at each layer, and that's perfectly doable.
Okay, thank you. Are there further questions? Do you see a question? I currently don't. So let me ask a question. So I think you partly answered this. So in which applications do we clearly gain over conventional convolutional neural networks? I mean, for example, does it make sense to also apply graph convolutional neural networks to applications where traditionally traditional convolutional networks have been successful? Does it?
That's a great question. The question is basically, where are we to gain from using GNNs as opposed to CNNs? And I will add RNNs. So CNNs have been mostly successful on images, right? And that is because the convolution operation on images is very well defined. It's very easy to compute, right? We have like all these techniques, so it's very easy. There have been tons of attempts to use GNNs on images. I hardly think you will ever beat CNNs. So definitely, I would not use GNNs on images. Not that you couldn't, yes, you can, but I don't think you will gain much because CNNs are already very powerful there. The other realm that is kind of settled is time signals, right? Typically audio signals. They are RNNs as well as CNNs, but mostly RNNs have been very successful. Same thing because they are exploiting this structure of having one time instant after the other. So in all of those cases, you could implement GNNs, you won't gain much. Where you will get GNNs is when you have a problem that is naturally described with a graph structure. Right, so as I was saying in the introduction, wireless communications, power grids, robotics, sensor networks, like there are many, like traffic coordination, right? When you can have like this idea that you have nodes that only exhibit pairwise relationships, that's where you should be doing GNNs in particular, graph signal processing in general.
Okay, thank you very much. So there's a question by Atta Khalili. Is your graph learning method able to compute the graph similarity matrix? Would you please explain?
That's also a great question. So the graph that we described in terms of S, so far in this talk, we have always considered that that graph is given, right? It's given by the physical structure of the problem. If that is not the case, you can go ahead and estimate the graph. And there's like this huge literature on like topology inference of the graph. So you could like first obtain your S and then go ahead and train your GNN. And you know, because of the stability result, that as long as your estimate is good enough, what you are training will work on your network. That is like one pipeline of doing this, which is I use topology inference to estimate S, and then I run my GNN. One of the GNNs that I mentioned that is a non-convolutional GNN is the EdgeNet. In that case, you could learn the graph at the same time that you're filtering. So that would be a second option. So to sum up, I have assumed that I know S, but you don't have to. There are ways of learning S as well.
Okay. So there's another question by Shosha. are there specific learning properties for graph neural networks, or are they the same in usual neural networks?
Great, thanks. Yeah, these are all great questions. So GNNs are, as every other whatever NN, a particular case of a fully connected neural network. So in principle, saying things for neural networks, unless you restrict too much what your linear transformation is going to be, you're going to get results, right? Like that could translate. But what I think it's a very exciting area of research is, what does the graph structure buy you that you don't have when you look at a fully connected neural network, at the DNN or MLP or multi-layer perceptron, whichever name you want to put. So I think, and that's what I'm willing to do now, what I'm starting to do now is like, what does the fact that you have a given data structure, how does that help you in your learning process? Instead of doing the opposite, which is I just pick the most generic one, and then I try to understand why the optimization problem gives me a good result.
Thank you. So Lucas Chinol is asking, how can we effectively ensure the integral Lipschitz property in the training of graph convolutional neural networks?
Great. So because your graph is finite, your spectrum is finite. So in that spectrum, by definition, all filters are integral Lipschitz, right? Regardless of that, what we want is also to control that value of C in the integral Lipschitz. And one way of doing that, and in fact, it's the way we're doing it, we add a penalty on your loss. So if you can see, you can write that lambda H prime lambda in terms of the filter taps, and you add that as a penalty during your training, and that works. In fact, that's the way that we have done it in our journal paper of stability. So basically a penalty.
Okay, thank you. So Yu Yang Li is asking, does transferability from network of size 50 to size 100 mainly result from using imitating learning framework?
Good. So the short answer is no, or the short answer will be no, but I'm not sure. So we have seen transference in problems where we don't use imitation learning. I think that transference becomes on the structure of your graph, of your convolution. So basically, we observe the transference because even though the graphs have different size, they are very similar in their spectrum because they are all what they are called planar graphs, right? In all of these graphs, which is like throw the nodes at random and connect them based on distance. So they all come from the same family of graphs. And I believe that's exactly what's giving you transferability. What's very interesting that we observed in another robotics problem, the path planning problem, is that there is a threshold. So there is a minimum number of agents that you need before you scale, right? So we observe this phenomena where, when you start with very little agents, let's say 2, 4, 8, you won't scale to 100. But once you reach a certain threshold, let's say I think it was 10 or 12, you immediately transfer to much larger networks. And basically you don't see. And this threshold phenomena is definitely interesting, and we don't have like a good idea on why that is happening.
Thank you. So Yang Cheng is asking, in the last part of your talk, do you have guarantees of stability and performance for the GNN controller from imitation learning?
That's another great question, and I think it's also a good research area. So the short answer is no, because we didn't impose a model on how the matrix S changes with time. For us to be able to use the stability results that we have, we kind of need to assume that ST won't be far from ST minus 1. That is definitely a very interesting question. That is definitely a very interesting area of research. I think that there are two things to leverage to answer that. One is all the models that we have on dynamic graphs, right? And how we can impose a model on how the dynamics of our graphs are changes. And on the other hand is like the graph filter that I chose is one very specific, but there's like this whole literature of time varying graph filters that can also be very helpful in answering that question.
Thank you. So are there any further questions? I don't see currently. That's your last chance. If you want to ask a question.
You can always reach out to me by email. Happy to keep talking about this.
Okay. So I think there are no further questions. So I thank you, Fernando, for your great talk. I thank all the attendees for participating here. And I hope to see you next Thursday for the talk by Merwan Debar. Okay, so I say goodbye.